here. Welcome everybody. Those who came late, I can see a lot more people have been joining. Welcome to this, I don't know, presentation this year of the Astronomical Society of Botswana. And I'm very pleased to introduce Mike Bode, who is the emeritus professor at of astrophysics at Liverpool John Moores University, and now a visiting professor of astrophysics at the Botswana International University of Science and Technology, and also advisor to the Astronomical Research Institute of Thailand. Mike is no really stranger to many of us. He has presented quite a number of presentations. I must add that he is the founding chairman of our society here. So our very presence is here. We are grateful to his leadership in that regard. And I think without much further ado, I would like to give Mike the floor. You can see the title there. Is there anybody out there? It promises to be a mouth-watering presentation. We're all looking forward to it. Mike?
Okay.
Take the floor.
Well, thank you. Thank you, Matsupatsi, for that very nice introduction. And it's very nice to be here. And I see we've got some people attending, not just from Botswana and UK, but also the United States. Some old friends from there have got up slightly early and are now joining us, so that's great. So is there anybody out there? This is a personal view, as you'll see. Although it delves into things at very great distances in our own Milky Way, it also has some relevance to things much nearer to home, as I hope you'll see. So I call this subtitle, Personal View of Humanity's Greatest Question. So I'll give you an overview of the talk. We're going to talk about our galaxy and the search for life, the search for intelligent life in our galaxy, the Milky Way, and Fermi's paradox. And I'll tell you a little bit about that if you don't already know. Then the search for extraterrestrial intelligence. And I'm going to do something I don't very often do, I guess, which is I'm going to show you equations, but I'm only going to show you one equation, but I'm going to show it to you several times, and that's the Drake equation. And we'll get quite familiar with that as we go through, and you'll see why. A very important part of this is the lifetime of a technological civilization such as our own. And here we'll touch on things much nearer to home. Then I'll run the numbers, see what we come up with, and then there's some conclusions and a final word. I have to say that this talk was inspired by a recent article by my old friend and colleague, Doug Whittet, who's emeritus professor at Rensselaer Polytechnic in New York these days, but we were colleagues in what's now the University of Central Lancashire. And the background here is the Taurus molecular cloud, and Doug led observations that I was very pleased to be part of ice and ice coatings on dust in that molecular cloud. And he became eventually the director of the Astrobiology Institute of New York, retired from there a few years ago now. But there's an inspiring article he wrote, and I probably won't do it justice, but it was the inspiration for this talk. Okay, so the Milky Way, those of you who are privileged enough to live in a country where you can get away from light pollution fairly readily and you have a lot of clear skies will be very familiar with the Milky Way. Those of us in the UK don't see it quite so often. Some kids don't see it at all because they live in cities and we have a lot of cloud. But anyway, this is this Milky Band that can run if you're on a very dark site, a dark night, dark clear sky. It runs from horizon to horizon. This Milky Band with as is shown in this image here, which is actually from the Southern Hemisphere, a dark lane running along it. This is the European Southern Observatory with the 8-meter telescopes, and the laser you can see there is what's called a laser guide star. It produces an artificial star in the sky, and through various wizardry they can actually use that to improve the image quality of the images they're taking. But if you were to look at the Milky Way from outside, this is what it would look like. So it's a large spiral galaxy. We're sitting about 2/3 of the way out, somewhere in a spiral arm, just on the edge of a spiral arm, about 30,000 light years from the center. So you can get an idea of the scale of this. There are between 100 and 400,000 million stars in the Milky Way. And those of you, a lot of you will be pleased to know there's a bar in the middle of the Milky Way. It's actually a barred spiral galaxy. Okay. At our position in that galaxy, by the way, as I said, about 30,000 light years from the middle, we take over 200 million years to go around once. So from the time of the earliest dinosaurs, we've only been around the center of our galaxy once. So both in time and space, this is an enormous structure. Let's move on to Fermi's paradox. By the time we get to about 1950, the scale of our galaxy was reasonably well determined and its content was reasonably well known, not as accurately as we know it now, but they had a very good idea about the dimensions and the vastness of the Milky Way and the number of stars it contained. Around this time, in fact, going back to the end of the 19th century, when Percival Lowell was seeing canals on Mars and speculating that these were formed by a civilization living on the planet that was taking water from the ice caps to the arid regions of the desert and watering Martian vegetation. So there was a lot of interest in extraterrestrial life, intelligent life. There was obviously the War of the Worlds and all those other works of fiction that were written from the end of the 19th century onwards. But particularly in the end of the 1940s, there was a spate of flying saucer observations, incidents, and so on. Flying saucers like this one, photographed over a farm in Oregon, caused quite a stir, except these looked very much like hubcaps thrown up in the air, and a lot of them were. In fact, there are very, very few of those observations or sightings that remain a mystery. All of them can be explained one way or another. But in 1950, they were making headline news. Now, Enrico Fermi, whose picture is on the right-hand side here, was a pioneer nuclear physicist, a pioneer of nuclear power, was also involved in the development of the atomic bomb at Los Alamos National Lab in New Mexico. He was also involved in the subsequent development with Edward Teller and others, Hans Bethe and co, famous physicists, in the development of the hydrogen bomb. And I should say that by the time we got to about this point, not very many planetary scientists thought there really were canals on Mars, and we now know that Mars is a very arid place without vegetation, let alone canals built by another civilization. But Fermi and his compatriots used to have lunch at Fuller Lodge, and I spent 2 very happy years working at Los Alamos, and a couple of years subsequently as a consultant to the lab. I've been back a few times since, and at least one of the people on this call is an old friend of mine from Los Alamos. So this is Fuller Lodge. They used to go there for their lunch. And you might recognize this interior. This is the interior of Fuller Lodge, which these days is like a community center and a small museum and so on. But in those days was a cafeteria and a social center. So one day in 1950, Enrico Fermi, Edward Teller, who was the father of the hydrogen bomb, was still around in the days when I was working at Los Alamos. You'd see him occasionally in the canteen. They were having a conversation over lunch when they were interrupted by another colleague, I think it was Professor York, who was a visitor, who'd seen that morning a cartoon about flying saucers in the New Yorker magazine, and they're all having a bit of a laugh about this. But Enrico Fermi said, well, maybe we could work out roughly how many civilizations there might be in the Milky Way. As I said, they had a reasonable idea how big the Milky Way was, how many stars it contained, and this back of an envelope or napkin calculation showed to Fermi that there should be an enormous number of these civilizations in the galaxy. But they didn't believe any of the sightings of UFOs, or they didn't believe that there were, extraterrestrial craft visiting us. There was no evidence at all of visitation. So the big question was, where are they? Since then, since the 1950s, there have been various searches for radio signals, because that's the most likely way that we're going to get contact from an extraterrestrial civilization. And this has been organized now for 3 or 4 decades through the SETI project, which uses arrays of radio telescopes, sometimes large single telescopes, and in the future will use the Square Kilometre Array. They're searching for radio signals from other civilizations in our own galaxy. And these days, they're able to aim at particular stars with particular star systems where life, perhaps intelligent life, is more likely to have evolved. And we'll talk about that a little bit more in a moment. In the future, this project will use the Square Kilometre Array, an observing project, the like of which, a ground-based project, the like of which has never been seen before. It's the largest ground-based observatory ever built, and Botswana is very much involved in this, as those from the society will know from previous talks. But nothing has been seen yet. There was a signal in 1977, a chart recording, which has been labeled the WOW event, seemed to be inexplicable as something from nature, but that never came back, has never been seen again, and maybe it was some strange interference or something, we don't know. Anyway, nothing so far. So why is that? Why have we not actually found, verified the existence of other civilizations in our galaxy? There are possibilities here. The origin of life and the emergence of advanced life are extremely improbable events, perhaps even unique to our planet. And this is the so-called rare earth hypothesis. The other possibility is that civilizations are common, but they choose for some unknown reason to keep their presence hidden. And this is the so-called zoo hypothesis. And that's something I've favored in the past, I have to say, but let's see. And then the third one, which is a bit bleak, is that technological development is inevitably accompanied by a tendency to self-destruct. And this is the apocalypse hypothesis, that we don't just, our civilization doesn't live long enough for there to be, or typically civilizations don't exist for long enough for them to be very many at any given time in our galaxy. So let's see whether we can actually calculate how many civilizations there might be out there. And this is where the Drake equation comes in. Frank Drake was a radio astronomer in the United States. He started, I think it was called Project Ozma, which is one of the first searches for extraterrestrial intelligence using the radio part of the spectrum. And he met, or a meeting was called, rather, between him, Carl Sagan, Philip Morrison. These are all big names in astronomy at the time, and others, including a biochemist who, during the meeting, got a phone call from Stockholm to tell him he'd won the Nobel Prize in chemistry that year, which was quite an event during the meeting itself. But they got together, they got their heads together and decided how they might calculate how many civilizations capable of communicating there were in our Milky Way galaxy. And this is the so-called Drake equation. And this is the equation he's got on the board behind him there. And we'll go into that in some detail now, taking each of those terms in turn. So this is the Drake equation. It gives you an answer in terms of the number of advanced civilizations there are currently, or likely to be currently, in our galaxy, capable of communication, radio communication particularly. And there are 7 terms on the right-hand side. Now, Frank Drake came up with a neat way of, a neat analogy for this. So, for example, if you want to find out how many undergraduates there are in a university, in the whole university or in a university course, you can say, what's the rate at which they're entering the course? And this is this rate of star formation on the left-hand side. And then the right-hand side, the rest of the right-hand side, rather, those other 6 terms, are basically how long those undergraduates stay in the university. So you've got a rate times time, which will give you a number. And it's each of those terms is what we'll consider in turn now to see whether we can define, how well we can define each of those terms and come up with the number n on the left-hand side. So bear with me for a few minutes while we go through this. I have to say that as you move towards the right-hand side of this equation, the terms become more and more uncertain, generally. But let's have a go. So the first of these terms is that rate of star formation. And this is one of the most well-defined terms on the equation. So the star formation rate in the Milky Way, and this shows a region which is fairly typical of where new stars are forming. They form in molecular clouds, like the Taurus molecular cloud I showed you earlier on, in the Orion Nebula, which you are probably all familiar with in the sky. This is a region in the Eagle Nebula called the Pillars of Creation, and this is a JWST image. The HST image was stunning. The JWST image is incredible. So the estimated rate of star formation in our galaxy comes out to between 1 and 2 solar masses a year, and that's pretty well defined. So this is probably the best defined of the factors that we'll be considering. So remember that, about 2 solar masses a year. Now, those stars are not all stars like the sun. Most of them have a lower mass and a longer lifetime than the sun. Some of them have a higher mass and therefore a shorter lifetime than the sun. But the sun is you know, it's a reasonably typical star. It has a very long lifetime, about 10 billion years. It's about halfway through its lifetime. And those are numbers that we'll come up against in a few minutes. So the next factor here is the fraction of stars in our Milky Way which have planets, because advanced civilizations or life itself, you think, is more likely to evolve on a planet than anywhere else. Now, if we went back 30 years, maybe a bit more, we didn't know for certain about any planets around other stars. There were hints from the wobble of one or two stars as they move through the sky, but nothing definitive. And then through various challenging observational techniques, but actually some of them using very small telescopes, the sort of telescopes that amateur astronomers have, we discovered the first so-called exoplanets, planets around other stars. And since then, we've discovered many more. In fact, we have a whole zoo of exoplanets. Many of them are more massive than the Earth for a couple of reasons, because one of the techniques of detecting exoplanets is to do with occultation. As a planet moves in front of its parent star, and the bigger the planet, the bigger the effect of that occultation is going to be. The other way of doing it is to use spectroscopy to look for a wobble in the star caused by a planet going around it as the star moves backwards and forwards in our line of sight. And obviously, the bigger the planet, the more massive the planet, the more that wobble is going to show up. So we preferentially detect more massive planets. A lot of these planets are gas giants like Saturns and Jupiters, Neptunes and Uranuses. But now we're detecting rocky planets down to Earth-like masses. And as of last week, there are 5,800 exoplanets that have been catalogued and verified. So it's likely that most, if not all, but most stars in the Milky Way have at least one planet, and many of them have extensive planetary systems. So that number, the fraction of stars with planetary systems, could be approaching 1. What about the number of habitable planets per system? So now we want to look at where in that system a planet may reside, where it could be habitable. And for life to evolve, as far as we're aware, you need liquid water. And liquid water is only going to survive at a certain range of temperatures. Too cold, it's going to freeze. Too hot, it's going to evaporate away. And that gives you as the so-called Goldilocks zone or habitable zone around given stars, where it's not too hot and it's not too cool. It's just right for a planet to retain liquid water. And if you look at the bottom image of these two, this is our own solar system. Venus is on the inner part of the habitable zone. It's pretty hot. And Mars is in the outer reaches of the habitable zone. It's very cold. In this system called TRAPPIST-1, which was discovered a few years ago now, multiple planets, of which at least 3 are in the habitable zone of this star system. And the star there is a much less massive star than the Sun, a low mass red dwarf star. And therefore it's much lower luminosity. So the scale that we're talking about of the TRAPPIST-1 system is much smaller than our own solar system, but at least 3 of the planets there seem to be in the habitable zone. So, and we've found quite a few other planets in habitable zones around their parent stars. So maybe that factor is reasonably high as well, because we do find a lot of multiple star systems, multiple planetary systems around stars. Let's move along a little bit more. Now we're getting a little bit more uncertain as we move to the right. The fraction of habitable planets, so those in that Goldilocks zone, which actually have life. We haven't managed to, we don't understand still the transformation between complex chemistry and life. It's obviously happened, as far as we're concerned, here on the Earth. It either occurred on the Earth or the Earth was seeded with life. This is a mural from the NASA Ames Center in California. And it's a sort of artistic impression of comets bringing complex chemicals to the Earth, a lot of volcanism going on, primitive oceans and the tree of life springing up. But the Earth formed about 4.5 billion years ago, not too long after the solar nebula itself formed. And then it is thought it was suitable for life about 4.3 billion years ago. The earliest fossils are 3.7 billion years old, but a very recent paper using genomics has determined that the last universal common ancestor of everything was around 4.2 billion years ago and could have existed slightly before that. So, I mean, we're talking about hundreds of millions of years here, but it's a relatively short time interval now between where the Earth was suitable for life and it's here. So, either the Earth was seeded with life from outside, or the formation of life is almost inevitable, given the right circumstances. And this abiogenesis from complex chemistry to life is thought to occur in these deep sea hydrothermal vents. As as an aside, I did mention in one of these talks that if it happened then, is it actually happening now? I don't know whether it's possible to determine that, but it's an interesting thought. So maybe this factor isn't as low. Maybe this isn't as unlikely as we might first think, just looking at that. Now the big question, what's the fraction of those planets with life that develop intelligent life? Well, on our own planet, aside from ourselves and the great apes and so on, there are other intelligent beings. The dolphin, very intelligent. Octopuses, apparently very intelligent. They separated, they have a common ancestor going back about 200 million years. And then they evolved quite separately, but the eyes and so on, the evolution of the eye is quite remarkably similar between different species that only, separated so long ago in evolutionary terms. So maybe it's almost inevitable that you will end up, given the right circumstances, enough time, you'll end up with intelligent life on a planet. Maybe that factor is quite high as well. The difference between dolphins, octopuses, and ourselves, there is a very subtle difference. If you talk about building things, we have an opposable thumb. We can actually make things, construct things. Dolphins probably made, in hindsight, a very poor choice to go back into the ocean all those millions of years ago, because as they are, they're never going to be able to develop anything in terms of a technological civilization. So that brings us on to the fraction of civilizations that might or a fraction of planets that might develop the technology for interstellar communication. So our earliest radio broadcasts are now out to about 100 light years, which is this tiny little sphere down here. I don't know whether you can see my pointer, but anyway, that little blue dot there, superimposed on this impression of the Milky Way, just shows what a small region of space that is. But within that 100 light year radius sphere, there are hundreds of stars. Our most powerful radio transmissions could be detected at about 12,000 light years. So if another civilization had something as powerful as the radio signal that was sent out from Arecibo, this very large radio dish, a couple of decades ago, we could see it from 12,000 light years away. And 12,000 light years is actually the distance that Harold told us that NGC 2158, the globular cluster, is away from us. So we could see that sort of transmission from a goodly fraction of the stars certainly in our region of the Milky Way. So millions and millions of star systems. And the final factor in all of this is the lifetime of a technologically communicating civilization. And here we use ourselves as the analogy or the guinea pig. So what are the limiting factors for us on Earth? How long is L going to be? And this is a diagram from Doug Whittet's article. It shows the imminence from very low, so the incidence is rare, to the incidence being high, and it takes into account to some extent the actual impact of these things on our existence, effectively. On the left-hand side are the natural causes, and on the right-hand side are those over which we have more control. And I'll go through these in turn. So the evolution of the sun. The sun formed around 5 billion years ago, and it then it steadily got to a point rather where it settled down to steadily burning hydrogen to convert to helium. And it's been doing that for several billion years. It's actually around 30% more luminous now than it was when it first settled down to what's called its main sequence lifetime. And in about 2 billion years, its luminosity will have increased steadily to the point where the habitable zone that we talked about before will have passed beyond the Earth. So this gives us an upper bound to the lifetime of the civilization on the Earth, because the Earth will not be habitable beyond that point. But that's a long, long time. So what about a nearby supernova or gamma ray burst? We see supernovae in external galaxies. The last supernova that we observed in our own galaxy was in 1604, although it's reckoned that we should observe one roughly every 50 years. There might have been one or two that have been missed since then. None of the stars in our neighborhood are likely to turn into a supernova which will threaten the existence of life on Earth. Similarly, these even more energetic objects, outbursts called gamma ray bursts, and none of those, they're very rare in our Milky Way galaxy anyway, and none of those are likely to threaten us. In the fossil record, there's only one event that I've come across which possibly was related to the explosion of a nearby supernova or gamma ray burst, and that was about 250 million years ago. So these are very rare events, and so the risk is very low from these. It's not quite the same for comet and asteroid impacts. So these are bodies in our solar system which are orbiting the sun. They can get disturbed from their orbits, thrown into the inner solar system, cross the Earth's orbit, and the Earth might and has collided with them in the past. It might do in the future. It has done in the past for sure. And here is an object in this video, which is a compilation from dashcam videos and security videos in houses from Chelyabinsk on the 15th of February 2013, so almost exactly 10 years ago. There were 7,200 buildings damaged in Chelyabinsk. Nearly 1,500 people were hospitalized because of flying glass. This was an object that was around 20 meters or so across, I believe. It exploded about 30 kilometers up. It had the energy during that explosion, so something like 30 times the Hiroshima bomb. But these sorts of impacts are pretty rare. There was one in 1908 from a larger object that demolished thousands of square miles of forest in Siberia, and this was in the Tunguska event in 1908. The size is reckoned to be between 50 and 100 meters across, and the frequency is perhaps every few hundred years. The Chislub, if that's how you pronounce it, event, the crater in the Gulf of Mexico, that is where this asteroid is thought to have struck 65 million years ago, was around between 1 and 10 kilometers in size, but the frequency of those events is much lower, thank goodness. And currently, the JPL Sentry system, which is monitoring the output of observations of asteroids and comets where the orbits have been well determined, doesn't show anything like a Tunguska event that's likely to happen in the next 100 years. Although, you know, things do change, objects are discovered, and as time goes on. So this is the so-called Torino scale. This is a map of the kinetic energy or size of an impactor and the probability of impact. And it goes from small objects with very low probability of actually crossing the path of the Earth and hitting the Earth to very large objects in the top right-hand corner with a high probability of hitting the Earth. And on the Torino scale, this goes from 0 to 10. If you look at the Sentry website, and I've given the Sentry website here, there's only one object at the moment that shows up on the Torino scale. And this object has a Torino scale number of 3. So if we look at that, it's down in this region here with a reasonable probability, but it's not a very big object. It's thought to be about 60 meters across. The probabilities of it striking the Earth in the next 100 years, I guess in 100 years. Oh no, it's in that date interval there, 2032 to 2071 is about 2%, something like that. So it's worth watching it, but it's unlike a lot of the press reports which have dwelt on this object recently. It's certainly been on the BBC. There is no significant threat from it. And this is an observation taken from New Mexico Tech in 27th of January of this object. And if you were to take a series of images, you'd see it move against the background stars. And the more positions you've got with time, the more accurately you can determine the orbit and therefore define rather better whether it's going to hit the Earth or not. And at the moment, there's nothing that we know of that poses a severe threat. Supervolcanoes. This gets interesting. I knew very little about these before I started to read around this talk. About 74,000 years ago, in Lake Toba, in Indonesia, a supervolcano erupted that has left this large lake. Some of the fallout from that has been found in various parts of Africa, by the way, and some of the research on the fallout from this comes from Malawi, for example. It liberated 3,800 cubic kilometers of what's called dense rock equivalent, of which 1,800 cubic kilometers was ash. It gave rise, according to some scientists, although this is debated among the scientific community, a nuclear winter, which lasted perhaps for decades. Now, the estimated mean frequency of devastating supervolcanoes erupting is about 80,000 years. That doesn't mean the next one's going to erupt in the next 6,000 years from now. That's an estimated average timescale. So it might erupt next year, it might erupt in another 80,000 years, but on average, that's what it's felt to be. And this could have a devastating effect on the Earth's climate as far as cooling is concerned, leading to something like this nuclear winter that the eruption of the supervolcano that formed Lake Toba led to. So, I think Yellowstone National Park is sitting on a supervolcano, so and of course it would affect the whole Earth, Anyway, so perhaps one to watch. Natural climate cycles. There are ice ages, and the image here that you can see is the Earth as it was at the end of the last ice age. It's about 25,000 years ago, plus or minus a few thousand years. And this is the ice age temperature changes, or temperature changes over time, and this is over hundreds of thousands of years up to the present day. We're actually in an interglacial at the moment, where the Earth is relatively warm. It's been warmer in the past a few times. It's been a lot colder in the past as well. And these ice ages seem to be periodic and related to changes in the Earth's orbit and the tilt of the Earth's rotational axis, plus an added effect of greenhouse gas emissions from tectonic plate movements. That is another factor that comes into this. So it's not just completely regular cycle. I guess it affects it in some way. But where I'm sitting now, I was walking on a beach near here yesterday, and that's the end of a terminal moraine from a glacier that was here at the end of the last ice age. And maybe 80 miles from here, the city of Birmingham was under several thousand feet of ice in the last ice age. So this is the northern hemisphere, by the way, and it would have affected the south as well, although most of the landmass is actually in the north. So climate cycles are something that would give rise to a huge disturbance to a civilization, but they happen rather slowly, and it'll be quite a long time before we go into the next ice age. Global pandemics, these have happened many times. They're very likely to happen on few generations timescales, hence it's red in this case. And they have devastating effects. The Black Death killed a third to a half of the population of England and a third to half of the population of Europe in the 15th century. And there were plagues before that in the Roman Empire, which actually one of them might have led to the decline of the Roman Empire. And there have been various plagues since. There was the Spanish flu in 1918 to 1920, where more people died than in the First World War. But none of them have put paid to civilization. We've always survived, come out of it, and continued. And that, plus medical advances and preparedness, make the threat from global pandemics rather less. So I hope that's a positive note. Some of these things are slightly negative. Let's go on to human factors where we do have some control. Nuclear war, artificial intelligence. I suppose artificial intelligence, if it is allowed to run away with itself, and you end up with self-replicating machines that don't see the value of human beings, then that's where artificial intelligence might cause the end of civilization. Nuclear war, obviously, a full-out nuclear war would probably not kill everybody on the planet. We'd have to start all over again in some way, but could be really devastating. And there's this website where the doomsday clock, which is, I won't go there if you want to be cheered up, but anyway, this has been advanced in the last few weeks because of the situation in Ukraine mainly. It was set up originally by Einstein and Oppenheimer just after the Second World War, or at least the organization that runs this was set up by them, and then the Doomsday Clock is the face of that organization. Bulletin of the Atomic Scientists. What about climate change? This is where we get really down to earth. The mean global temperature over the last 2,000 years, by indirect and direct measures, has been shown to have been fairly stable until we entered the Industrial Revolution in the last couple of hundred years. And the mean global temperature has just shot up. At the same time, you can see that the amount of CO2 that's been put into the atmosphere by human activity has also shot up. The two things seem to have mirrored each other. Now, you can have cause and effect that are not related, but in this case, there's a lot of science behind the connection, a lot of modeling that does show this connection. I used to be very skeptical about this sort of thing because, you know, the Romans were growing grapes further north than I'm sitting now, with grape varieties that were not as hardy as the varieties we have these days. So the climate was fairly mild 1,500 years ago, milder than it is now in Great Britain. But these are natural climate cycles. This is something that's being caused by human beings, and I became convinced, my mind was changed by supervising a project student who was working on this some years ago, and then spending some time among climate scientists in Parliament a few years ago. I spent a week with them, and yeah, we are warming the world. And we could end up with a planet rather like Venus, which has seen a runaway global warming, so that the surface temperature on Venus is now 460 degrees centigrade, Celsius. And at the surface, which this is a Venera image from one of the Russian probes that landed there and survived an hour or two, that surface temperature is so high that lead melts. Because of the greenhouse effect on Venus, even though it's further away than the sun, from the sun than Mercury, its surface temperature is actually higher than that of Mercury. Mercury is close to the sun, but is slightly cooler than Venus. And we get to a tipping point eventually where, if we keep on increasing the temperature of the Earth, forest fires become more common, You get rid of the vegetation in that way. The sea, the warmer sea, is less likely to be able to absorb as much carbon dioxide as it does now. The ice caps start to melt and the reflectivity of the Earth goes down, and therefore more heat is absorbed from the sun, and it leads to a runaway effect. So it is quite, it is quite worrying and challenging. And just to show you, this is from Whittet's article. These are the main sources of carbon dioxide, or greenhouse gases in general, and it's energy generation, whether it's for power for our homes, or whether it's for electric vehicles, whether it's for vehicles, transportation in general, including air travel. That's the major part of this. I was sitting next to, just by chance, the Senior Vice President of IATA, Mary Owens Thompson, coming back from Botswana about 18 months ago, and we got into a conversation. And I asked her in preparation for this talk, air travel seems to be a real challenge to make air travel carbon neutral. But according to Marie, if we spent enough money in research and development, we could make air travel carbon neutral by using new fuels, by using new propulsion systems. We can make them carbon neutral by 2050. So even in the case of air travel, it's possible to end up with something that's carbon neutral. This I found to be a very interesting plot. This plots the economics of energy production for different types of energy production methods. And you notice that there's an enormous drop in the cost of solar panels over this 10-year period, making them far more economical than any other source of power. And it struck me that, and wind power as well, has also followed a trend in that direction. It struck me that there's something positive there for Botswana, but let's move away from the negative thoughts that I've just been expelling and talk about some positive things. We fixed the ozone hole. Remember, the ozone hole was this big threat, particularly in the southern hemisphere, probably about 20, 30 years ago. And when CFCs were banned, this is gradually closed, and that problem has gone away. Acid rain, leading to the loss of foliage on trees, for example, in Norway, due to pollution coming across from the UK, has almost been eliminated due to international action by putting reactants that absorb sulfur dioxide in smokestacks of coal-powered power stations. And it isn't too late to reduce our carbon footprint by international agreements. And actually, I've come to realize that by using renewables, I know there are challenges there, but you're less held hostage by outside powers when you rely on your own resources for power generation. And looking at the rapidly evolving costs of different energy generation sources, it seems to me that Botswana is the ideal place to lead in solar power. You have a lot of sun, you have a lot of land. So, I believe that these projects are happening actually in Botswana, but it just struck me that looking at that graph, it's an ideal place. Okay, well, let's get back to the astronomy. Running the numbers. This is the Drake equation. You can find an online calculator, so you can put your own numbers in this. It has default settings. And these are optimistic ones. This is a realistic number here. It goes through the fraction of stars with planets, which we think is quite high. The fraction of Earth-like planets is probably quite high. Fraction of those with life, if we're optimistic, that's quite high. Intelligent life is 50-50. Communication is about 20% of those. And if a civilization lasts for 100,000 years, then you get 12,000 and more civilizations in our galaxy right now capable of communication. But it might be optimistic. And as you move right on that equation, as I said a few times, it gets more uncertain. But if we retain the optimism of all the other factors and set L to just 100 years, in other words, through our own actions or through some cosmic catastrophe, civilization on the Earth only lasts for 100 years in a way that it can communicate. So this is a radio transmitting and receiving civilization. You get 12. So it's a big range. Okay, so we started a bit late, and I know that we're running slightly late now as a result, but just to wrap up, personal perspective, I'm optimistic that life elsewhere may be detected in the coming decades, either in our solar system, directly from probes, or by spectroscopy of the atmospheres of exoplanets using facilities like the James Webb. There's no evidence yet of contact by extraterrestrial civilizations, but the search goes on, and what a transformation that would cause. The lifetime of our technological civilization, most of the existential threats are beyond our control, but aren't imminent, except maybe this super volcano, which is sort of news to me. I'm a bit more gloomy about the threat of nuclear war and out of control AI than I was a few years ago. But I'm still tending to be on the optimistic side, nevertheless. I mean, if things really went pear-shaped with AI, and they did, AI took over the world and did away with humanity in terms of self-replicating machines, maybe in one sense we would live on in AI and go on to colonize the galaxy. But I think that would be a very sad outcome. Human-induced climate change can be brought under control, and probably will be, but only with more concerted action. And doing so, the path to get there has some benefits, I think. Communicating technological civilizations are rare, but it's rather too soon to say we're alone in the Milky Way. And it's anti-Copernican, the thought that we are in some way in a special place or unique seems to go against everything that we've learnt about our place in the universe over the last few hundred years since the time of Copernicus and the Earth going around the sun. And then, just a final word, this is from Doug Whittet, if we're the only technologically advanced civilization in the galaxy, let us sustain that status with pride. If we are not, then let us live long enough to verify it. And with that, thank you very much. And thanks for bearing with me while I had the technical problems at the beginning.
Oh, thank you very much, Mike. Really fascinating. I think we'll open the I can see a lot of satisfied gestures, but I'm not seeing any question, no hands up. But let me just run through the guests. Nobody has his hand up. So
I don't know how to put my hand up. I'd just like to make a comment.
Yeah.
That was
I
fascinating.
think yeah.
Harold, yeah.
Okay, go ahead.
Okay.
Go ahead.
Okay. That's fascinating, Mike. Thank you very, very much. I worked on a diamond mine in Namibia 50 years ago.
Yeah.
And there were 6 beaches which had been formed over many millions of years.
Mm.
We then thought it was 10 million years because the diamonds had been brought down from the interior of Africa down to Namibia, the coast, and then washed up the shore. But the interesting thing was there's 6 beaches, and those beaches were formed by the sea rising and then falling, transgressing and regressing over the millions of years.
Yeah.
The best diamonds were on the 6th beach. We called it the F beach. The 6th beach, which was the oldest one, which was very interesting, I thought. And that sort of time, I thought, linked into what you were saying about the cyclical nature of the heating and cooling of the Earth.
Yeah.
I just thought I'd make that comment.
Yeah. Well, no, that's very interesting comments actually, Harold, because obviously the ice ages led to a big decrease in sea level with all that water locked up in the poles, and I think sea level went down by a few hundred feet. So there are land bridges where it's open ocean now. So big changes over a period of time, and that's really interesting. I'd like to know more about those beaches actually, Harold, if you get a chance to send me some info of it.
Okay, I'll do that.
Thank you.
Oh, thank you. I see a hand by Dr. Sipa.
Yep.
Please say.
Yep.
I think your mic is muted, Dr. Sipa.
Oh, thank you. Actually, I have some bit of a connection problem, so I don't know if I'm going to be audible. But I wanted to thank Professor Bode for his wonderful talk. It was quite captivating and quite insightful. But I just also wanted to add in terms of expanding maybe our understanding or something of that sort of life, because I wanted to talk about the Goldie lock zone, to say that sometimes we can have a planet which is quite far away from some heat source like a sun, but it would have its own heat sources, probably from gravitational forces and stuff like that, so that life may arise in a region which is not particularly a Goldilocks zone. And the other thing would probably be to open our minds for possibilities of life that can arise from a solvent, which is not necessarily water. But on final point, I would just like also to add, because personally I have experienced 2 types of extraterrestrials. So for me, it's not a matter of whether they are there. So I would like to agree with the comment that you made initially, when you started, that probably they are around us, but they don't want to be seen. I will agree with that, because usually when I see them, they are not really kind of visible, and they can also go through walls. And I've seen 2 types. People talk of more than 24 types I've only seen two. But when I read ancient scriptures like the teachings of Thor, like some people call him Tahud or Dahud or something like that. But Thor, he talks of these beings and he says for one to see them, we must use sound. So I was thinking perhaps if we also want to maybe detect them, we can use a bat technology, the technology that bats use of seeing with sound. That is all. Well, wonderful talk. Very, very wonderful talk. Thank you very much.
Well, thank you very much, Dr.
Thank
Sipper, for that. Yeah, for those very interesting thoughts. Yeah.
Yeah, very, very interesting. I think
Oh, Farmy, you got your hand up.
I've
Sorry.
really become learned today. Yes, any other comments or any questions? I
Farmy?
think without really more. Oh, okay. This FM, I don't know. Fami.
Yeah.
Yes,
Please
it's
come on.
funny. Okay.
Yes.
Yeah, thank you very much. And a very interesting talk, Mike. I'm happy that these topics that were sort of seen to be in the fringes before can now be discussed openly. I just have a comment to say there's been footage that was released from America, and there's a certain David Fravor. I believe he's a fighter jet pilot. And what they did was using instrumentation inside the fighter jet, they were actually able to image phenomena. You know, it was this thing that was flying and it seemed to defy the laws of physics. So I'm just bringing it to everyone's attention just to say, go ahead and check it out. It's quite interesting footage. I'm not sure how I feel about it, but yeah, it could offer some insight into some of the statements that you've made here in your final word, Mike. But yeah, thank you for an interesting talk.
Thank you. Yeah. I've got a couple of comments there. First of all, a lot of the UFO flying saucer sightings are around military test sites, like the White Sands test site, where it was actually in the interests of the military to have people believe that they were seeing spaceships, not actually prototypes of military vehicles, aerial vehicles. The same in this country, actually. But there may be a small fraction of these things that aren't easily explained. I gave a talk once to a bunch of people that includes some RAF pilots, and they said they'd seen things that they couldn't really explain. But then again, even the most experienced observer can be misled. I have to tell you this anecdote from Jodrell Bank. They have, which is a big radio observatory not far from here. They have a call the astronomer. If you have any questions, get in touch with them and they'll answer them from the general public. So they have the most frequently asked questions, and they have their most frequently given answers, which is the joke. Their most frequently given answers are, "It's Venus," and the second one is, "No, it's Venus." Not a spaceship. So anyway, yeah.
Oh, yeah. So if you are finished, Mike, it's it's quite late after the 1930. So
Prof,
I think at this point,
his hand up.
Oh, I've got Bill. Okay, Bill, please come in.
Hi, Bill.
Bill, you've got your mic muted. Maybe you're talking.
You're right. Sorry. Mike, nice to see you.
And you, Bill.
Thanks for
an entertaining and thought-provoking talk. I quite enjoyed it.
Thank you.
I was just going to ask what you think about, I noticed everything was sort of limited to the Milky Way galaxy.
Yeah.
And if I sort of understand things correctly, we look at the number of stars in the Milky Way. Well, there are probably more galaxies in the universe than there are stars in the Milky Way.
For sure. Yeah. Yeah.
So has anyone tried to take what you were talking about, the different variables and so on, and then expand it to how this might play out in the universe as a whole?
Yeah.
And then I guess I'd even add on top of that, if we're not even in a single universe and there are other multiverses all around the place,
Yeah.
this really could turn into a question of, well, I had a professor who liked to tell us that, you know, the more you learn, the more you realize how little you know.
Yeah.
And
Yeah.
I've always tried to keep that in mind when I think I'm getting onto something.
Yeah.
But that thing of going from the galaxy to the whole everything.
Yeah.
Has anybody really tried to tackle that problem, as far as you know?
Well, I think the thing is there that this was set out to see whether we should be spending time looking for signals from other civilizations. And if you expand it beyond the Milky Way, then you know that the power that you're going to need to generate an artificial signal is going to be much, much greater. And secondly, you know, I talked about being able to observe our signals from Arecibo, for example, 12,000 light years away. You send out that signal, and then 24,000 years later, you get a reply. So, you know, if you're going to do anything practically, as it were, then you want to confine it to your own neck of the woods. You could do those calculations, and it would come up with, well, on the other hand, the uncertainties would be even greater, I suppose. But yeah, no, it's an interesting thought. I mean, the one thing that I've thought is where I had some sympathy with this, you know, zoo. The second possibility that these are so advanced, these other civilizations are so advanced that they don't really have much to do with the southern observers. You know, we might be on the verge of understanding what dark energy is, and there's some theorists that think that dark energy is related to other dimensions, several other dimensions beyond the four that we experience. And if you're beings that have actually cracked that and move around in umpteen, well, nine or whatever it is, dimensions, what we do here is absolutely trivial. So maybe that's what it is. I don't know. Anyway.
Well, you know, as a fisherman, standing on the shore of a big lake and standing there for hours casting my bait out and not getting any bites.
Yeah.
Especially when you're with kids, you know, it's pretty soon like, Dad, there aren't any fish in this lake.
Yes.
And I say, well, we can only cast our bait out about 10 meters or so, you know.
Yeah.
So
Yeah,
maybe
yeah.
we drive around the other side of the lake, and that may take us some time before we can drive around to the other side of the universe, but could happen.
Yeah. You know, I think it's foolish to say things are impossible, you know, so because
Exactly.
time and time again in scientific history, it's proved not to be the case. So, but anyway, yeah.
Anyways, thanks a lot, Mike. Nice to see you.
Oh, thanks, Bill.
Okay. Thank you very much for those comments. I think we should be closing the session now. It's almost 1952. So I wish to thank Mike, and I would like to also thank all the participating, guests, audience, just to make this a very interesting evening. Thought provoking and quite elucidating. So I think with that, I wish to say no, thank you. We are meeting again in about a month, and to also try to learn something, and we'll continue to do so. So thank you very much for everybody for your patience, and till we meet again.
Thank you,
Mike.
Thanks, everybody. I'll see some of you in the committee meeting immediately after. So,
Thank you.
Yeah. Okay. Thanks. Night, everybody.
Thank you. Bye-bye.
Oh, bye.
Thank you.
Afternoon. Good evening, Dr. Tsipa. Good evening, Dr. Tsipa. Good evening, Dr.
Hey,
Tsipa. Oh, you heard me?
how are you? My network is not very good here. I
Oh,
don't know
it's
if you are going
okay.
to be able to hear me nicely.
Now, I wanted to say thank you for the link.
All right.
So, are they going to view the
Yes.
planetary alignments tomorrow?
Yeah, no problem.
I'm saying, are they going to view the seven
Sorry?
planets alignment tomorrow at